Thank you very much. In first place, I would like to thank the organizers for the opportunity to give this talk in this very nice conference in Vienna. Today, I will talk about an extension of the infrared triangle that is well known in electromagnetism and general relativity beyond Lorentz symmetry. In particular, I will describe it in a Fracton gauge theory, the same that Christian described in the previous talk. This work was done in collaboration with Ali Seraj and Stefan Prochaska here, and is based on this article. Well, the infrared triangle in electromagnetism and gravitation basically connects three seemingly different infrared phenomena: of theorems, asymptotic symmetries, and memory effect. These three phenomena, they have are based on the same basic infrared structure, and are different manifestations of the same structure that is behind. Okay, and for the moment, was only defined for this kind of relativistic theories. So a natural question that we had at some point: okay, can we extend this kind of structure beyond Lorentz symmetry to consider systems that are non-relativistic? So this was basically our questions, and we explore this question, this kind of Fracton gauge theory. Why this Fracton gauge theory? By many reasons. In some way, this theory shares many properties with electromagnetism and general relativity, so are very close to both of them. I will explain in detail in what sense. And we were able to show that the triangle exists, and in particular, we found a novel memory effect that we called a double kick memory effect, because it's very similar to the one of electromagnetism, which is called kick memory effect. But now, I will explain in detail why the name double. We also found an infinite tower of soft charges of asymptotic symmetry associated to this problem, and a new type of soft theorems that we call it dipole soft theorems, because will be associated with theories with dipole conserved moment, as Christian discussed. I will do a very, very brief review of fractons because, was very well explained in detail in the previous talk. But in few words, fractons are quasi-particles with limited mobility. If you have a system with this kind of excitation that cannot move in any way, basically we're talking about fractons. So there are many different models of fractons, and they were introduced in the context of condensed matter. One particular property is that in general they are non-relativistic. By that reason, were good toy models to explore this question. If we're able to observe this infrared structure beyond Lorentz. In particular, in some models, in my opinion, the simplest one, the restricted mobility is associated to the presence of a new symmetry. In the models that I will consider, there will be electrically charged particles, so the total electric charge will be a conserved quantity. But in addition, there will be an extra symmetry that leads to a conserved dipole moment. This is in contrast with electromagnetism, where the dipole moment is not conserved. Okay? So if we want to have a conserved electric charge and a conserved dipole moment, we need a conservation equation of this form with a current which is described by a symmetric tensor with two indices. Why? Because if we take the time derivative of the dipole moment, this means that the time derivative will act on the charge density. So if we replace the conservation equation here, we integrate by parts twice, one can show that d dot is 0, so the dipole moment is conserved. This is the reason why we need this kind of conservation equation. A direct, yes. Yes. Yes, because if you consider, for example, electromagnetism coupled to non-relativistic matter, at the end of the day, the soft theorems are insensitive to the hard sector because they are universal. So at the end of the day, in practice, it will be the same computation that Weinberg did. So there is nothing. Yes, indeed, nothing new will appear. It will be exactly the same soft theorems. The idea was to play with a toy model that is close enough to electromagnetism, but not the same. So that was the motivation. Okay, so a direct consequence of the conservation of the dipole moment is that electric monopoles are immobile. They cannot move. Why? Because if we take the time derivative of the dipole moment, implies that the velocity of the monopoles are zero. So monopoles are completely immobile. They cannot move. However, dipoles can move freely, but always maintaining their orientation by the conservation of the dipole moment. Okay? So in this sense, we have a fractonic behavior. Now, some known systems with this kind of fractonic behavior are the following. There are some models of elasticity that describe the dynamics of some topological defects. In particular, the phonons that describe the interaction between these topological defects are dual. The theory that describes these phonons is dual to the electromagnetic theory that I will show you later. Okay, so this was described in a very nice paper by Pretko and Rasidowski. Another very interesting system, but I think it's still not well understood from the point of view of fractons, is the dynamic of vortices in superfluids. If you have vortices, by the conservation of the vorticity, of the center of vorticity, you can show that they have a very similar fractonic behavior. For example, you can create a dipole made out from two vortices that rotates in opposite directions. I can show you, if you want, in the coffee break, how to create a dipole made of vorticity with a cup of coffee. It can be easily done. So the idea is to understand better this kind of system, but they have fractonic behavior, which is what we're interested in. This constrained mobility was also has been suggested as a promising approach for quantum information storage because they have restriction to mobility, so it's expected that they are will resist better the external perturbations, okay, to save information. But my personal motivation is more theoretical, and as Christian explained very well, these are very puzzling objects as they defy some of the standard methods of quantum field theory. So even from a purely theoretical point of view, it's very interesting, in my opinion, to study them. Okay, this is one of the systems that Christian showed, was introduced by Pretko, and consists of a complex scalar field, where we can see that, well, one can add different potentials. Here I consider the simplest one, just adding a mass term. But you can see that the free theory doesn't have special derivatives, so it's Carrollian, this piece, okay? And one can introduce this potential, which is invariant under this transformation. As Christian explained, the first piece corresponds to a global U1 transformation, and in addition, one has this symmetry, which leads to the dipole conserved charge. Okay, this is one of the possible models. There are different models, but this is the simplest one. Yes, it's the same. Was the same symmetry? Was exactly the same. In one of the models, yeah. It's global. Okay. Yeah, it's a global symmetry. Yes. Yes, one particular example just to show, one model. But and in addition to this, the electric charge and dipole moment, the theory is also invariant under space and time translations, as well as spatial rotations. But what is important is that there are no boosts in this theory. By that reason, it's called an Aristotelian symmetry. And why there are no boosts? From an intuitive way to see this is because we know that monopoles are immobile. But suppose that you have a boost at hand. If you apply a boost, in principle, the monopole can move, but we know that this is not allowed by the symmetry. So an alternative way to see that the monopoles are immobile is that there are no boosts present in this theory. And in particular, if we combine the space-time symmetry with these two extra symmetries, one can show that the algebra with these non-vanishing commutators is isomorphic to the Carroll algebra plus one additional central extension, where the role played by the Carrollian boost is now played by the dipole moment, and the Carroll energy corresponds to the electric charge. And the energy of the fractons is the extra central extension. So there is almost a one-to-one map between the Carroll algebra and this dipole algebra. Well, this has been explored in different papers. And one can describe a sort of fracton-Carroll correspondence in the sense that one can map many properties of one's Carrollian system to fractons and vice versa. But I'm interested in describe the infrared sector of the theory, and in particular the radiation. So the next step is to couple this system or any of the other possible models with conserved dipole symmetry to gauge fields. So as Christian explained, a natural way to do it is to associate to the charge density a scalar potential like in electromagnetism, but now to the current density a symmetric tensor potential, a potential which is a symmetric tensor, in such a way that the coupling of the interacting terms take this form. So the dynamics of these gauge fields was a model that described the dynamics of this field was proposed by Pretko, and the Lagrangian has this Lagrangian, which is, as you can see, is very similar to the one of electromagnetism. But now we have an electric field with two indices, now and a magnetic tensor with three indices. But one can directly show that these quantities, the electric and magnetic fields, are invariant under this gauge transformation, where the scalar potential transforms with the time derivative of this gauge parameter, like in electromagnetism, and the symmetric tensor transformed with two derivatives of the gauge parameter. This is in some ways similar to the case of linearized gravity, where the metric, the spatial metrics, also transform with two derivatives. So as you will see, shares some property with both theories. We have a symmetric tensor like in gravity, but also has a very similar structure as electromagnetism. Now the equation of motion are these ones. The first one is the Gauss law. It's a constraint. It's a constraint that generates the gauge transformations. In addition, we have the current that describes the time evolution of the electric field. Okay, if we want to describe the radiation, the first step is to decouple the equation of motion to find the radiative solutions. Usually in electromagnetism or in linearized gravity, what we do is to write the equation of motion in terms of the potential to find an appropriate gauge fixing. We fix the gauge in an appropriate way, usually the Lorentz gauge or the Donder gauge, and in that gauge, the equations are naturally decoupled. This is not so easy to repeat this approach in this case because the equations are more complicated and we don't have enough gauge freedom. It's subtle, but a systematic way to do this is to decompose the fields into irreducible components of the rotation group. For example, the electric field can be decomposed in this way: a transverse part, a transverse sector, which contains three fields, let's say two transfer and traceless and one trace. The TL sector, which is transfer longitudinal, which contains two independent functions, and the waves will be contained in these two fields. And the purely longitudinal component is completely determined in terms of the charge density due to the Gauss law. So it's exactly the same as in electrodynamics. The longitudinal component is fixed by the Gauss law, and the transverse components, or TL here in this case, contain the formation of the waves. The corresponding projections can be implemented by using standard projectors. Here the hash symbol denotes a T or TL, depending on the situation. But what is interesting is that if we use this decomposition and we implement it in the equation of motion, one finds that the equations are decoupled, as one expects, but one can show that both components of the gauge field, the transverse and the TL components, obey wave equations. This is very non-trivial because the system was not relativistic. Why do we observe a wave equation? But in practice, this is what happens. But a very curious thing is that there are two speeds of propagation. The transverse modes propagate with speed c, which was the coupling constant in the action. But the TL modes propagate with speed c tilde equal to c over the square root of 2. This is because the theory is non-relativistic. Of course, in a relativistic theory, this is impossible. But in this kind of model, is very usual. A very well-known example, for example, are earthquakes. Earthquakes, they have two different polarizations, basically transverse waves and longitudinal waves. And longitudinal waves moves faster than the transverse ones. So they arrive first, but we are not, unfortunately, we are not able to feel them. But dogs and birds, they can. So they know 20 seconds before the earthquake will come 20 seconds before. And later, a couple of seconds later, the transverse waves arrive and destroy everything. But it's exactly the same phenomenon, okay? Another interesting consequence that is very unusual at least from the relativistic point of view, is that there are two radiation zones or null infinities. So when we connect this with asymptotic symmetry, we need to explore them independently on each region. Okay, so the next step is to find the analog of the linear Wigner solution. But now the problem is that monopoles do not move because they are immobile. So they will only generate a Coulomb field, but will not emit radiation. However, one can study the case when we have dipoles moving in a certain trajectory, and to compute the radiation field emitted by the dipole. So one can look at the textbooks in electrodynamics, and one finds that the charge density of a dipole takes this form. So from the conservation equation, one can read the form of the current tensor, and take this form. And what is interesting is that now it's easy to see why it has two indices. Because one index is associated with the velocity, like in electromagnetism, but the second index is associated with the presence of the dipole moment, which is a vector. So by that reason, we need two indices in the game, okay? And since we have the wave equations, we can use the standard green function that we use in electromagnetism. So one can find the analog of the linear Wigner solution, but for dipoles. And one can see that it's almost identical to that of electromagnetism. The only difference is in the numerator, where now we have the dipole moment, okay? But it's very, very similar. And now with this solution, we can start to play. So let me describe the first corner, the memory effect. From the solution, one can see that the asymptotic behavior of the potential is this one, goes like 1/r, like in electromagnetism. And now the idea is to consider a scattering process of n dipoles. So we will have in the far past n dipoles, free dipoles. They will interact at some point, and in the far future, they will be free again. So one can compute the change in the potential from the far past to far future. And this is this quantity. And this is called the memory, and will be the most fundamental object of this talk, because all the expression at the end of the day, all the physical quantities will be expressed in terms of these memories. And of course, the transfer component contains transverse projectors of the dipole moment and the velocity, and the TL components, transverse and also radial projections of the velocity and the dipole moment. Okay, so we have the scattering process. The radiation was emitted during the scattering, and if we consider a test dipole which is very far from the source, will receive the radiation and will interact with the Fracton electromagnetic field through a Lorentz force, a generalized Lorentz force that was also introduced by Predko, which is this one. And so if we replace the form of the electric and magnetic field for this configuration at leading order in 1/r, one finds a net change in the velocity, which comes from integrating this equation in time, from an initial to a final time. And so we observe, like in electromagnetism, a kick memory effect, where there is a change in the velocity, not in the position like in gravity. But now, since we have two different waves with different speed, will be a double kick memory effect. Because if we have a dipole, we'll receive at some point the first kick, and after some time, we'll receive the second one. So it's very similar, but we have this new feature. Okay, let me do a very brief analysis of asymptotic symmetries and boundary analysis of this system. As I said, there are two independent null infinities associated to T and TL sectors. One null infinity is defined when R goes to infinity, but this quantity T minus R over C remains finite in that limit. And the second null infinity is defined when this quantity T minus R over C tilde remains finite. Okay? So we need to perform the analysis for at each sector independently, but most of the equations are very similar. So basically, I will use just one set of equations to describe both sectors, and I will show you the difference when there are. For example, the electric field in spherical coordinates has this fall-off, which is consistent with this fall-off for the potentials. Here, these fields are very important because we will contain the information of the waves, the leading order of RA, which will be the TL wave, and a bar AB, which is the T sector, the transfer sector. And also the scalar potential, the leading order is proportional to R, and contains here the total electric charge. So in the T sector, as I said, the TL component of the leading order vanishes, and all the information of the wave is codified in the purely transfer sector, which depends on this quantity, which are the analog of the bond in use for this system. And on the other hand, in the TL sector, they depend on the TL component, the RA component of the electric field, and this is the corresponding News tensor associated to this sector. So this asymptotic symmetry, this asymptotic condition are preserved by this gauge parameter of this form, and the transformation of the field is this. Okay, so we have three parameters, lambda, eta, and epsilon. And if we compute the charges, you can do it using your favorite method. One find three pieces. The first one contains only a zero mode, and that corresponds to the total electric charge. And one finds two infinite towers of soft charges, except by the mode with L equal 1 of P, which correspond to the dipole moment, the conservation of the dipole moment. But the rest of the higher multiple moments correspond to the soft charges associated to this system. And one has to impose some condition on the gauge field in such a way in order to have a finite charges and finite energy, which are these ones. And well, since there is radiation, the charges are not conserved, and they obey some flux equations. And for example, as expected, the time derivative of P and Q on each sector depend on the corresponding news, bond in use. And if we integrate this equation in time, one can see that the change in the total flux of the charges depend on the memories. Or another way to see this is that the memory effect can be seen as a large gauge transformations. This is the form of the gauge transformation that I showed you before, but with this gauge parameter, which are completely determined in terms of the memories, the delta TL, delta AT, whose expression is this one. So now we connected memory effect with asymptotic symmetries. So there is one missing corner, which is the soft factor. What are the soft factors? Well, the soft theorems have a very long history. They were introduced by Lowe and Weber by the end of the 50s and the 60s. And the idea is if one has a scattering process with the emission of one soft particle, the amplitude factorizes into the amplitude of the purely hard sector without the emission of the soft photon or graviton, plus a factor which is called the soft factor that depends, which is divergent in the soft limit when the frequency goes to 0. Now we don't have scattering of particles, we have scattering of dipoles. And therefore we will describe the dipoles, the incoming and outgoing dipoles they are labeled by their momenta, which will be the mass times the velocity, and the dipole moment. And there will be the emission of one fractonic soft photon, which is labeled by the frequency and the corresponding polarization. So we expect a relation of this form, okay? To derive the precise form of the soft factor, we will closely follow the approach of Strominger and Siboyedo, where they started from the memory effect, and they were able to derive the soft factor. So, okay, this computation followed very directly that of Strominger and Siboyedo, so I will not go into the details. But basically, what one has to do is to expand the gauge field at very large distances to obtain the leading order, the 1/r expansion. And using a saddle point approximation, one can show that take this form once it is expanded in Fourier modes. So if we have this expression and we compute the change in the potential, which is the memory, using this identity, then one can show that the memory is proportional to the creation and annihilation operator of a soft photon. So what we have to do is to insert this operator into the amplitude, and one can show that the amplitude will factorize in terms of a soft factor that depends on the memory. This is the exact form of the dependence of the soft factor in terms of the memory. And so if we use the expression that we know for the memory, we find the following soft factors for each sector, for the T sector and the TL sector. So with this, we close the triangle. But you can naturally ask, okay, you found some factors, some factors using this approach, but how do we know that they are correct? Is there any alternative way to derive the factors? For example, in the case of electromagnetism and gravity, Weinberg and Lowe, they use Feynman rules. They use Feynman rules to derive the soft factors. So the question is how to derive the soft factor in an independent way to check. Yes? Well, yes. Yes, it's a good point, because there are different ways to close the triangle. One of them, what I did is to start from memory effects and to derive a soft factor. Okay. The other possibility, what Strominger did in one of his first papers, was to start with the form of the charges and to derive the soft factor as a word identity of the associated to this symmetry. We haven't yet completed that computation. We're doing that computation. Will appear hopefully soon, but everything indicates that it will work in the same way. It's very similar, but as you said, one has to add the current, the hard current to the conservation equation. But yeah, it's still in progress, but I think it will work. Yes, but it's a very good point. So the idea now is to perform a cross-check to determine if these soft factors are correct or not. But it's not so easy as in field theory, because now we're considering the scattering of dipoles. And dipoles are not elementary objects in this theory. They are bound states. So basically, we need to find a way to describe the interaction between bound states. And in general, this is a very hard task even in quantum field theory, because one has to take into account the interaction between the elementary excitations and all that to construct this bound state. So we spent some time on this, but finally we realized that there is a way, at least for the purpose of computing the soft factors, there is a way to circumvent this problem of this abstraction. And it's the fact that one expects, in analogy with electromagnetism and gravity, that soft factors are universal, because they are associated to symmetries, okay? So they must be independent of the theory that describes the hard sector. So in principle, if we are able to find some model, any model, it doesn't matter if it is realistic or not, if it is useful or not, if we're able to find one model that describes the effective dynamics of the dipoles, which is compatible with the symmetries, one can in principle to compute the soft factors. So what we did is to construct a very, very simple model. The way to do it is to take two monopoles and to glue them together using a very particular potential. I didn't write the details here, but I can show you the details if you want later, with a particular potential that is depends on the moment of the dipoles. And after some field redefinition, after some redefinition of the variables, one can show that a model that describes the dynamics, at least of the free part, is this one. So it's basically the kinetic term of a standard non-relativistic particle plus a term that contains the dynamics of the dipole moment, and here B is the canonical conjugate to it. And one can couple this system to the electromagnetic, to the Fracton electromagnetism by using the charge and current densities that I showed you before. So one can construct this, let's say, particle action for a dipole interacting with this fractonic field. Okay, but this is not a field theory, so we need to find a field theory associated to this system. We need to quantize, to perform a first quantization of the system. There are many ways to do it. A simple way is just to write this Lagrangian as in a gauge in such a way that is invariant the time parametrization. So one obtains a constraint, and if we impose that this constraint, following Dirac, that this constraint annihilates the wave function, one finds the following wave equation, which is nothing but that Schrödinger equation with this particular coupling, okay, with some minimal coupling. Now one can see immediately that this wave equation can be derived from the following Lagrangian. So now we have a field theory model. It's an effective field theory model that we constructed by hand, but let's compute the soft factor associated to it. So the ingredients that we need are, yes? Yes, it's a degree of freedom. Mm-hmm. Yes. Yes, the wave function in general depends on T, Z, and D, but the constraint does not depend on the conjugate, B. So at the end of the day, it's a degree of freedom, but will not appear directly. For all the purposes, it can be considered as a fixed quantity because there are no derivatives with respect to D in the wave equation. Sure. Exactly, because by the conservation of the dipole moment at the end of the day. Exactly, at the end of the day, yes. So the ingredients that we need, because we want to compute the soft factor, I'm a bit out of time, but it's basically that we have the scattering process with of hard particles. And what we need is to consider the insertion of a soft photon. So we need to introduce a vertex. It will be the soft photon. So we need a vertex, and we need the propagator here of the hard particle. So one can see from this action that the propagator takes the standard form of a of the propagator of a non-relativistic particle. And the vertex, the only vertex that is associated with the emission of a single soft photon is this one, which is quadratic in the fields, in the hard fields, and proportional to the tensor potential. This is the vertex. So basically, if we compute this extra contribution to the amplitude, and well, now one must be careful with the values. If you assume that the external particles have, the external particle is, let's say the photon has energy omega and momentum, this momentum, and that the external dipole has momentum p, then if we replace this quantity, the propagator, with the vertex, one finds this expression, but in the soft limit, when omega goes to 0, this expression reduces to this one. And if we project this with the corresponding polarization tensor, we precisely recover the soft factor that we found before. So this is very reassuring in the sense that we use a very special model that we construct by hand, but the soft factor is precisely the one that we found previously. So it's very reassuring that the things are working well. The photon, yes. Yeah. No, I mean, what is independent of the details of the theory is the dynamics or the interaction between the dipoles and how they were interacting with the, let's say, the interaction and how they will interact with the electromagnetic field. But the data that one needs to include is that we have dipoles, free dipoles at far past and far future. Okay. I'm not sure if I understood your question, but okay, the dipoles are hard in the sense that they have mass. Okay, they are not gapless. They're no. But I don't understand very well your question. But so, I mean, yes. You can distinguish between hard and soft. Yes, I agree. But here you're creating alcohols. No. I'm creating. No. I'm creating annihilating photons. Let me go back to. No. This is the gauge fields, and these are the creation operators that we are introducing. We're expanding the gauge fields in Fourier modes, and they create photons. Yes, it's very similar to electrodynamics. Yes, and are gapless, so can be soft. Okay, so this is the last slide, brief summary and outlook. What we did was to derive a novel, an observable double kick, potentially observable double kick memory effect. This is one of the nice things of the memory effect that in principle can be measured. And people is doing an important effort trying to measure memory effect, for example, in gravitational waves, using gravitational wave detectors. One interesting point is that if it is possible, now we know that this kind of structure can be extended to non-relativistic theories. Maybe it could be, it is possible to try to construct some new experimental setups in theories where, with gapless mode, where one can measure the memory effect in an independent way, not necessarily in electromagnetism or in gravity. This is one of the, I think, interesting possible outputs. I'm not sure if precisely for this model, this was the first step, the first model, because it was close enough to electromagnetism. But in principle, I don't see any important obstruction to generalize this to other condensed matter systems, for example. So we have the double kick memory effect, the soft theorem, corresponding dipole soft theorem, and asymptotic symmetry. So we were able to close the triangle. We still need to finish the computation that you suggested to relate this directly to the word identities using the charges, but we're in progress, but everything looks well for the moment. And as I said, I think it's important that this structure is beyond Lorentz, because there are many systems that can be used to play with it and used to measure or potentially measure the memory. Here we focus only on leading effects, but one can also ask about subleading effects, subleading soft theorems, and so on. This is also, this infrared triangle is one of the bases of the celestial CFT program. So, but now celestial CFT program is based on the existence of the conformal symmetry, which is associated with the Lorentz symmetry. We don't have Lorentz symmetry, we have the infrared triangle. Is there any way to generalize this? Is the celestial CFT, the conformal symmetry fundamental in the description? I don't know, but it's a question, natural question. Another problem that we are partially exploring, or we expect to explore in the next few months, is to use this duality between fractons and elasticity, or the duality or the relation with vortices, to try to see if it is possible to create some experimental setup that can be used to measure memory effects, or, as I said before, to explore how this generalizes to other capless systems, and to see, okay, what can be learned from that. This is all. Thank you very much.